First, I will make a complete introduction of the Sustainable Development Goals. The Sustainable Development Goals, also known as the New Agenda for Global Action, was released by the United Nations in the 2015. It's a universal goal adopted by all United Nations member states in order to take action to end poverty, protect, protect the planet, and ensure that all people enjoy peace and prosperity by 2030. Here we call it SDG. It contains 17 general goals and 169 sub-goals, which focus mainly on the global economy, the society, and the environment. The 13 general goals are listed here on the left of this slide. The demonstrating science and the technology can be applied to several SDGs as is shown on the right side of that, such as SDG 6, clean water and sanitation, SDG 7, affordable and clean energy, and so on. The main research of our vegetation team is connected to SDG 13, protecting the terrestrial system. Here we can see the connection between some SDGs on the left column and some ecological indicators on the right column in total. 24 multiple indicators can be used to solve the SDG goals. Some vegetation parameter indicators like annual leaf area index, maximum fraction vegetation coverage, forest above ground biomass can be obtained through remote monitoring methods. So, by monitoring these indicators, we can help protect the terrestrial ecosystem, combat desertification and land degradation, and protect the biodiversity, which is the objective of SDG 15. Currently, we have produced below products based on remote sensing data, including NDVI, GLS, Atlas Area Index, fraction vegetation coverage, forest above ground biomass. These products have been published on the Global Change Research Publishing and Repository platform, and they are accessible to national and global users. To find these products, users can search keywords like leaf area index or NDVI. If users want to find products for related ratings, they can search keywords like stand and belt and road. The vegetation parameter products we have published are recently downloaded and used till October the 20th, 2020. The published statistics such as NDVI, leaf area index, and fractional vegetation coverage have been downloaded over 19,000 times. Here we list the names of some datasets and the website for downloading. Now let's see the advantages of our vegetation products compared to the existing similar products like Modis and GUA1 products. Firstly, the temporal resolution of music vegetation products are 5 days, while Modis products are 8 days, and the GUA1 products are 10 days. Secondly, since it is produced based on combined multi-source images, the music products have better spatial continuity than Modis and the GUA1. Thirdly, The LI algorithm of vegetation products consider the water vegetation needs the problem. Let's tie into the quality of LI by 50% compared with modest LI products for the pixel mixed with water. In summary, our product published has some advantages over existing similar products. In terms of application, the above vegetation parameter products we published were used to support the production of the global ecosystem and environmental observation annual report from China. From the GOR for 2014, 2015, and 2017, as well as the Green Report of China. Here is a map of the relationship between data indicators and related contents. Based on the four types of data, we can do ecological and environmental monitoring. Data produced by the multi-scale quantitative remote sensing products can be used to calculate the vegetation parameter indicators graphs with the red box, which can be used for monitoring the microstructure of the ecosystem. Based on the vegetation parameter products, we can calculate some main indexes like the annual LAI index, the maximum fractional vegetation coverage, and the anomaly. To get the ALAI index, we need to calculate the annual mean value of valid LAI during a year. The annual mean LAI represents the quality of vegetation use. To get the MFVC index, we need to calculate the maximum value of valid MVC during the year. The maximum MVC represents the best state of vegetation use. Anomaly is the difference between the vegetation characteristic parameters, such as the annual mean leaf area index, annual maximum vegetation coverage, and the average value of vegetation characteristics of the years. It is used to describe the spatial and temporal variability of vegetation use. The average value of 2010 to 2015 was reported and can be calculated based on the following reason. Therefore, by calculating above indexes, we can monitor changes on the vegetation. Below are some specific applications of these indexes. We can see from the pictures that compared to 2010, the total forest above ground mass in 2015 in East Asia and Russia increased due to afforestation and forest protection, while it decreased in Southeast Asia and Southern Africa because of deforestation and fire disaster. That means that the international organization should put all efforts in forest protection in Indonesia and Southern Africa. Here are two pictures for the distribution of normally ALI of Southeast Asia in 2015. We can see that the average area of tropical forest saw a significant fall in 2015, especially in Sumatra. This is largely due to the large-scale cultivation of palm trees in Indonesia and lack of protection measures in Sumatra. Because of the deforestation, forest fire, the tropical rainforest suffer from further reduction. Here are the effects of El Niño to grassland ecosystem. Grassland ecosystems are predominantly distributed in northern Russia, the Mongolia Plateau, southern Europe, southern Africa, and northern Australia. The El Nino in 2015 resulted in conflicting effects in different areas, and the annual ALAI dropped by nearly 2 to 4% and decline in rainfall in Central and Southern Africa and tropical regions in the north of Australia. The annual MFVC of the grassland increased by 8, 8% in the temperate grassland of Central Asia and the tundra in northwestern Russia due to increased precipitation. And the temperature rises in Siberian plateau saw an obvious decrease and is shown in the green region, which means a rise in the temperature. This leads to a significantly better growth of tundra and farmland in this area. For the grassland on the western bank of Volga River in southeast Russia, its MFVC dropped by 30%. The main reason for this change is the precipitation reduction, which leads to the growth of the grassland. The El Nino also caused a reduction of crop yield in 2015. Farmland ecosystems are mainly distributed in western Russia, Southeast Asia, South Asia, east part of East Asia, Europe, and South Australia. El Nino caused the drought and annual ALI decreasing in Europe, mainly influenced maize and wheat. South Asia, mainly rice, and South Australia, and resulted in yield reduction of maize, rice, wheat, and soybean in 2015. Here is the calculation of the saturated water vapor pressure difference, named VPD. We can see from the distribution of anomaly ALAI of Southern Africa in 2013 that crops yields in South Africa and Niger decreased significantly. It is especially apparent for the corn yield in South Africa. By analyzing the stress factors for light, temperature, and precipitation, we can see that the reading framed in red circle was mainly influenced by the precipitation stress, and the crop yield reduction in Southern Africa was caused mainly by a significant decrease in precipitation. This picture shows the distribution of annual maximum LAI of China in 2014. Based on the latest statistical data, we can see that of all the provinces in China, the vegetation in Heilongjiang province and Fujian province grew best, and the vegetation in Xinjiang province and the Tibet province were the worst. Possibly because the two provinces are located in drought or later areas, so they are not suitable for vegetation use. From the distribution of anomaly growing seasons of China for typical ecological areas, we can see that the variation of growing season for tropical mountains and temperate continual forests are relatively flat. This picture shows the trend of the ALAI of Sunday forest protection area. There is an overall tendency of increase by year. This means that the afforestation practice have achieved a good effect in the southern forest protection area. Here are the related drivers of our presentation product and corresponding implication. This is a simple introduction of our vegetation product in the wanting the ecosystem. This is the first part of my proposal. And then I will introduce a detailed training on how to produce the thematic map. In this section, I will show how to produce the thematic map shown in the previous section as an example. I will talk about it in the following 4 parts. Here are the 2 software used when producing the thematic map. Survey is used for the data pre-processing, and the ArcGIS is used in the map production. The second part is about the data download. The vegetation parameter product can be downloaded from this website as shown in the before section. Our published product can be searched by the keywords async or belt and road. Here are some examples of the dataset name and corresponding download link.
In this product, you have the one with collected you have data set with collected because I see that most of your maps does not cover the working
This dataset is mainly about the China and ASEAN, the Association of Asia, Southeast Asia.
We don't have a global map. We don't have a global map.
We have the global map also published in this website. This website, you can download it in this website. Then let's go to the next step, the data processing part. There are 4 steps in total. Step 1 is imaging of stack. Since the published product, the region is divided into many tiles. we should mosaic those tiles into one image based on their geographical coordinates. Step 2 is projection conversion. The projection of the product is converted from the sine projection to WGS 1984 for better effects of display. Step 3 is image grouping. The target area is extracted based on the vector diagram. Step 4 is band mass. The desired monitoring index such as ALAI and NFVC can be calculated based on the images processed by step 1 to 3 based on this band mass method. The sample in this video, the LAI product over China and the ASEAN for 2013 is used as a sample data. It can be downloaded from the following link. This is the sample data used in the next part. At first, this is the main interface of the array. At first, we can import the files. This is the file in the China and the ASEAN. Here are the total 40 tiles in China and the ASEAN. We can change the size and move the position of the image in the array, and they should be completed into one image for further processing. Then we can convert these tiles into one image by selecting the thickness mosaic. We can use the toolbox, select mosaic, thickness mosaic, and then the setting dialog will be dropped. We can input the tiles to be. We can input the tiles to be converted in this style. And notate the data ignore value and the gathering distance can be modified in this area for each of the images input in the header. The two parameters can be changed. Then in the color correction part, the histogram matching can be selected to get a better display. But if you want to get a current value of the image, don't select that part.
If you want to get both, please come again. So if you want to get both.
If you want to get a current value of the background, sorry. Then this part can do the edge filtering and This part can also generate seamless lines to avoid the seam between the images. And this to select the format of the output image. And this can select set the output name of the image. This can define the output background value, and we can select the output band. Here, only one band is in this image, so we only select the band 1. Then the image is generated. We can see that the files are consolidated into one big image, but the effect of the display in sign projection is not good. See large distort in this area of China. So we need to convert the sign projection to another projection for better display of this image. We will show the conversion in the next video. Here, by selecting the reflecting raster toolbox, we can do the project conversion. Here, also in the toolbox of this raster management and the project raster. And this is the setting menu of the array corresponding part. Let's select image to transport the projection. And this part is the parameter of the projection and the image. It is the upper left corner of the image, and it is the pixel size of the image. It is nearly 1000 meters, and it is the output size of the image. Then we can select projection. Here, WGS 1984 are selected. Then we can see that the style of the upper left corner and the pixel size are changed from meter to the degree, and the output X size and Y size also changed. Here is the parameter of WGS bus. Then we can select the projection method and the output format of the image. Here we select the output name of the image. Then it can be converted to the projection of WGS 1984. Here we can see that the size effect of display for this picture seems better. In the next video, we will extract the reading we are interested in for the detailed analysis of the corresponding reading. Here, we input before we extract the reading, we need a file. The file to give the reading of interest. Here, we use the vector file of Chinese border to extract the file of China. And that is the vector border of China. Then we can extract the region of China by using the vector file of border, selecting the subset that data from our eyes toolbox. Here is the toolbox. This is the vector file, and we can here is the vector file, and we can select it to change the size. And if we don't want to, if we want to mask the pixels outside the region of interest, we can set a background value of the masked background value. This is the fill value of the product, and this is the output file name. Then the region of China is extracted. The next
before you do the extraction, you need to check the unique value of the background. How do you set the background value? You need to check the unique value of the background.
The background value are set as the background value are set as 0 in the formal, and the fill value of the image is set as minus 3200 and 32,767.
Is it arbitrary or is it check it from the image or
Yes. Yes, it is the fill value defined in the published product. In the next video, the next video shows step 4, which is an operational step. For example, if we want to analyze the vegetation variation based on images from different seasons or years, we can do the calculation. Here is the bandmass tool. By selecting the bandmass toolbox, we can monitor the vegetation variation based on 2 or more processed images. And the impression can be defined by users themselves. This example shows a simple subtraction between 2 images. And the parameter B1 and B2 are the input parameter in the equation, and it can be selected to the corresponding band to represent the corresponding band. same, we set the output name of the value. Here, two images are used in the band maps. One is the 2000 and one is the satellite image in 2013, 208, which is shown in the before study, in the formal PPT, and the other is processed based on the same process of the study of the PowerPoint not shown in this case, and this is to calculate this is to calculate the difference between the 2 days, which one is summer and one is winter. Then we can see the result of the subtraction. From this picture, we can see that the LAI in summer may almost larger in winter. Programming based on the survey or IDL is recommended if lots of images need to be processed. After pre-processing of images, we can produce a schematic map based on the axis. This video shows the steps of schematic map production. Here first, we can add the data by into the axis main interface. Here, the images are shown in these images can be, we can give them colors based on their corresponding value. The images shown now is based on their corresponding value and give a corresponding color map. Then we can select this display background value to a certain value to a certain color. Then there are other methods to map the picture. The method for the unique values will give each value one corresponding color. Each value one color. And this classified method will given the color in different classes based on their corresponding value. Here, a total of 9 classes are set, and we select the red to green color. By pressing this button, we can set the break value of each point to set the detail of the color. From 0 to 1000 to 2000 and to the max of 7000. And then we can set the color of the different class. Here, the field value we labeled it is max speed, and the zero value we labeled it in our specific color, and take the value to as 0. And then we set the range of the LAI. Note that due to the LAI product multiply on scale factor 1000 in order to in order to reduce the memory space. So this the value of the image needs to be multiplied on scale factor 0.0001 to get its real value. So we label the product in the following form. And then select the offline and the open button. The image was then Then we can build the semantic map based on this view of the product of the activities. It is by changing the layout buttons, we can select the different page size based on this. Here, the position of the map can be changed in this page, and we can modify its position. Then we return back to the layout view, and we can add some more surrogate symbols to this map. For example, the landing of the map. In this file, we can set the number of columns of the landing. Here we can set the font size, fonts, and the detailed content of the landing. Here we can set the border, background, the drop shadow, get routing of the landing. Here we can set a detailed spacing between the title landing and the landing title. Then the landing will be added to the map. We can drop it to modify its detail size. By the same that we can use result to add the north bar. There are different kinds of styles can be selected. Also, we can drop the image to the desired Please. Here we can add the scale bar of the project of the solar map. It is the cell containing various units such as meters, kilometers, and miles, and so on. Then we can add a title for this map. Here is the title, and we can change the size and font of the title. Here we can select the different style of the font and the font size and the font content. And after this, we can we can export it into a GPT file by press the file and export the map. And this is the result GPT file in the map of the map. And this is a simple example for generating the schematic map. If a lot of schematic maps with similar input data need to be generated, programming based on the ASCII is recommended to generate the schematic maps in batch. Since the ASCII have the function of programming using Python. Then that's the introduction of how to create the mathematics map. Thank you.
I have some few questions. So what is the temporal result? Do you have it for only the 2 months for the 2 years before you have actually the database?
The spatial resolution of the map is nearly 1,000 meters, and the temporal resolution of the map is 5 days, and the difference between two maps is almost 200 days.
But not in different years, that's what I want.
Yes. Can be the same year, 2030. The comparison is the LAI variation between summer and winter. Also, we can compare the LAI product based on the same season but different years. We can subtract using the two units.
So in this case, for the annual LAI, you have for time, you have time to time information of 2006 maybe 2019.
Our group, one student in our group does this work, but it was not showing the office units is mainly for the education and simple example, so it was not shown here.
No, like I'm talking in general, like for the general database, that is now where you downloaded the data set from.
Uh,
Where you downloaded this data set to demonstrate to us. For instance, if I enter that database, can I get the data set for LAI, which is time series, like 10 years, something like that, not only 1 year. Because I think
now, the data published by our team is from 2010 to 2015, about 5 years.
not just about about cover range of 15 or only cover
5 years. This case is also 5 years.
data set for 5 years. That is from 2010 to 2016.
Yes, yes, you are.
Just get out. Thank you. Thank you. Yeah, and I have one additional question. Did you calculate the LAI for the individual, like land cover type? For instance, you have LAI for grassland, LAI for forest land, or you did it for the whole of like the total vegetation?
Since we can get the LI of detailed land cover information from the land